Welcome to Organic Chemistry Review Problems. The first problem we have is, I call this TP number 1. Originally I'd like to put these in turning point questions, but these were from old exams. I picked some old exam questions that were good to kind of survey all the material. And so we'll just work through these problems and hopefully you'll do some of your review. So consider a molecule of methyl fluoride, fluoromethane. What functional group or classification of compounds does fluoromethane belong to? Well, when you're solving these problems, the first thing you want to do is draw the structure. So fluoromethane, this is another reason why you have to have some level of vocabulary. So to master organic chemistry, you have to have the vocabulary, you have to have the structures, be able to draw the structures, and then you're going to have to be able to recognize different functional groups and rules, and apply rules. You also have to recognize reagents. And if you can do those 4 things, you should be able to master organic chemistry. Okay, so this is fluoromethane, because you know methane is just one carbon. What functional group or classification of compounds? These are alkyl halides. Alkyl halides are introduced in your Wade book in really chapter 6. This is chapter 6 when you do SN1, SN2 chemistry. So this fluoromethane, Lewis structures. So to do Lewis structures, you draw the connectivity and then you add up all the valence electrons. So fluorine is its group number 7, so it's 7 valence electrons. Carbon is 4, and hydrogen is 1, and we have 3 of those, so that's 3 times 1. And so that's 14 total valence electrons. And as you can see, each bond has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And that is the Lewis structure. You make sure every element has an octet. So CH has a duet because it takes 2 electrons to fill its outer shell. And then carbon has 8 and fluorine has 8. So that is a correct Lewis structure. You need to review Lewis structures in chapter 1, and I strongly recommend looking at page 9, and it's the common bonding patterns. So common bonding patterns are, I call them happy molecules, or they could be almost happy elements. And you're dealing with organic chemistry, so you're really only dealing with main group. So if you look at this on page 9, you see that carbon forms 4 bonds and 0 lone pairs. That's when it doesn't have to be charged. Nitrogen forms 3 with 2 lone pairs, oxygen 2 with 2 lone pairs, hydrogen with 1 and 0 lone pairs, and your halogens form 1 bond with 3 lone pairs. So you can see fluorine is a halogen, and it forms 1 bond and it has 3 lone pairs. Carbon has 4 bonds, 0 lone pairs. Hydrogen has 1 bond, 0 lone pairs. You have to be quick and really learn how to write these Lewis structures. Another review would be the electronegativity. Basically, fluorine has electronegativity of about 4.0, and carbon has about 2.5. So this electron negativity causes the electrons to push towards fluorine, and that creates a dipole moment. And so it says using a structure indicate the net dipole moment. So as you can see, I drew this net dipole moment here. using electron pushing, write an expression for the homolysis of CF. Okay, now this is vocabulary once again. Homolysis. Homolysis would be when a bond breaks. It takes one electron, so one of these electrons in this bond will go towards fluorine. You see the half arrow, and the other one will go towards carbon. And this happens in free radical reactions. And so what this looks like then is fluorine gets one of those electrons in that bond, and carbon gets the other. I just indicate those in blue that were in that bond. And they're neutral. Okay, so that's homolysis. That's what you have in free radical reactions. You do free radical reactions, I believe, in chapter 4. Chapter 4. And then using electron pushing, because you need to understand how to draw these electrons, because it's how we express certain things. Express heterolysis of the carbon-fluorine bond of chloromethane. So in this molecule, both electrons are going to go with the fluorine. And when this happens, carbon is left as a carbocation, and fluorine will then take the electrons from that bond. And I'll draw these in as the blue. And now fluorine gets a negative charge, and carbon has a positive. Notice too, when you're writing these reactions, on the reactant side, your overall charge is 0. That means your overall charge over here on the product side needs to be 0. So you got a plus and a minus, it equals 0. And so that's the difference in heterolysis. Notice we have a double-headed arrow here. Okay, it says, draw fluoromethane in a way that the dipole is indicated by partial charges. So here above, we drew it with a vector. In this case, you would just make the carbon positive and the more electronegative fluorine negative. And then the next question, does fluoromethane have, this should be primary, secondary, or tertiary carbons? And basically this is a primary. It actually would be a methyl. So I don't even really like that question. I would say this is a methyl. So the carbon is not connected to another carbon, so it's a methyl carbon. If it was connected to another carbon, one carbon, it would be primary. If it was connected to 2 carbons, it would be secondary. If it was connected to 3 carbons, it would be tertiary. This question is important because you need to recognize these molecules. Some of these molecules are compounds that you're going to be using. So tetrahydrofuran, sometimes you see this as THF. And tetrahydrofuran is this structure right here. It is a ether and it is a solvent. You use a lot of, it's a solvent that you would use for Grignards in the Grignard reaction. Okay, diisopropyl ether. This is another solvent, diisopropyl. So that's 3 carbons, 1, 2, 3. And that would be diisopropyl ether. It's also an ether solvent. A lot of your ethers are solvents, and these are low boiling points. 2-pentanone. Well, pentanone has 5 carbons, so we go 1, 2, 3, 4, 5. And then we double check, 1, 2, 3, 4, 5. And we say, okay, let's draw this again because I drew 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2 pentanone. So on carbon number 2, so 1, 2, 3, 4, 5, on carbon number 2, we make a ketone. Okay, so that's a double bond. That is a ketone. And we know this because of the O and E, 2 pentanone. Isopropyl formate. Isopropyl formate. Well, the ATE means it's an ester. And isopropyl is the ester part. Formate is for only one carbon. And the ester is this carboxyl group here. So the carbon is double bonded to 2 oxygens. Okay, and then isopropyl. So isopropyl is, we've drawn isopropyl already. It's 3 carbons, the propyl, and it's an iso group, kind of like a Y. So that's isopropyl formate, and it is an ester. And you need to recognize esters. If you do not recognize these structures and their functional groups, then you can't solve the problems. Okay, N-butanol. N-butanol. Well, the OA-OL means it's an alcohol. And the N means it's a straight chain. Hey, okay, N-butanol means there's 4 carbons. You can draw them like this if you want. I prefer to draw them like this. So 1, 2, 3, 4. N-butanol. Since it's not specified, it is on the end, on the 1 carbon. So N-butanol means it's an alcohol. Okay, the next one is propanoic acid. So we know we have a carboxylic acid. So propanoic acid. We have 5 carbons. 1, 2, 3, 4, 5. And propanoic acid, the acid can only be at the end. As you can see, there's the carboxyl group. And you have 5 carbons. 1, 2, 3, 4, 5. I'm sorry. I just drew pentanoic acid. Okay, so propanoic acid would be 1, 2, 3. 1, 2, 3, which would be propanoic acid. Acetylene, that is chapter 9, and we will be talking about acetylene. Okay, the next compound is acetylene. Acetylene is basically 2 carbons and 2 hydrogens, C2H2, and it's a triple bond, so it's an alkyne. These are kind of just some common names. Sec-butyl, sec-butyl alcohol, sec-butanol. So sec-butyl is 1, 2, 3, 4. As you can see, that's a secondary carbon because that carbon is connected to 2 carbons at 1, 2. So that's where the sec comes from. And then butanol, it's the OH is coming, the alcohol is coming off of the secondary carbon, and we have 1, 2, 3, 4. So that's sec-butanol. And let's see if I can give you a page number to look at some of these. So there's, I don't know why I have page 21. Let's see what's on page 21. Oh no. Okay. Tert-butyl bromide. Tert-butyl. So you need to see that this is a tert-butyl. 1, 2, 3, 4. And it kind of makes a T. And that is a tertiary carbon. 1, 2, 3. So that's a tertiary carbon. That's where the tert comes from. You have 4 carbons, so that's the tert for tertiary, and there's 4 carbons, so there's butyl, and then the bromide is coming off of the tertiary carbon. So that's tert-butyl bromide. And you would draw it like this. If you draw the carbons, technically you're supposed to draw in the hydrogens. Acetone. Acetone is a solvent that we use, and we also use it in the lab. Acetone is a common name for 3 carbons. This is acetone. And the ONE means it's a ketone, and that's the ketone. Trimethylamine, this is a base, and it's also a nucleophile. So trimethylamine, there's 3 methyl groups on the nitrogen, and if you notice here, nitrogen is one of those happy molecules. It has a formal charge of 0 because it has 3 covalent bonds and 1 lone pair. Then 1-butene. 1-butene is 1, 2, 3, 4 carbons, and then a double bond. So I'll write that down here again. 1-butene. The ENE, 1, 2, 3, 4. And I always go back and count my carbons. That's 4 carbons. And the 1 signifies that the carbon-carbon double bond is on carbon number 1, and this is 1-butene. The next problem is complete the following acid-base reactions. Now, acid-base reactions are located on this is the page 21, and that's through 32. This is chapter 1. This is very important. You've got to be able to recognize acid and base chemistry and acid and base reactions. It's very important to get a feel for the pKa table on page 25, because that actually gives you numbers and measurements so you can recognize the pKa's. So when you do an acid-base reaction, the equilibrium, and here these are all drawn as a reaction rather than equilibrium, but acid-base reactions are always equilibrium. So equilibrium arrows are like this, where it's further to the right, or it can be equal. This is equal. So you have your starting material and your products, and they're going to be equal. Or you can have more to the left, where they're starting material. But the way this is drawn for this purposes, it's just you're supposed to write the product as if it's one direction. But keep in mind, equilibriums are always either to the right and left. And the way you decide that is you got to recognize your acidic, your acid, on your reactant side and on your product side. And then you look up the pKa. And your equilibrium will lie to the highest pKa value. So your equilibrium goes to the highest pKa value, which is going to be your, that's going to be your weakest acid. So a high pKa value is a weak acid. So looking at these problems here, the first one we have, this is actually THF, tetrahydrofuran, and it's reacting with HI. So in this case, your lone pairs on your oxygen will go and deprotonate the hydrogen, and you will form a complex like so. Here, where's your acidic proton? It's on the acidic acid. This is acidic acid, and this is a strong base. So the strong base, the O minus, will come and deprotonate, and then you'll get sodium acetate and water. This one is sodium amide. Sodium amide. Some people call it amide. Basically, the sodium is a plus charge, and your NH2 is a minus charge. That's your base. And here your methanol, it will come and deprotonate, and then those electrons will go on your oxygen, and you get the sodium methoxide. It's actually how you get sodium methoxide, which is a good nucleophile, and you get ammonia. The next reaction is a Lewis acid. So boron has an unhybridized p orbital in which the electrons will, from fluorine are your highest, non-bonding electrons will actually go and form a complex. So you'll actually form like a BF4 CH3 plus complex. And then here we have methylamine, and you have HCl. So you're going to get CH3NH3 plus, and you're going to get Cl minus. Notice the plus and the minus cancel out to be 0. Here you have methanol and sulfuric acid. Now, if you look, the pKa value for sulfuric acid is a -10. And so what happens here is the sulfuric acid protonates, and let's see if I can get some space here. So you get CH3, CH2, OH2, and then you get HSO4 minus. So what is the pKa value of this? And a protonated alcohol. What is the pKa of a protonated alcohol? The pKa of a protonated alcohol. Do I have that anywhere? I think that I do. I want to say -7. Let's see, protonated alcohol. It's a -2.4. So -2.4 is a higher pKa value than a -10. So this reaction would go towards the products. For this problem, we are asked to draw resonance structures for the following intermediates or compounds. The first one is benzene. And benzene is this structure here. Now remember, resonance structure has the double-headed arrow. Resonance structures is section 1-9, and this is page 13. Now this is just the movement of electrons. The electrons in unhybridized p orbitals, so they have to be unhybridized p orbitals. These are pi electrons. They're capable of moving from one atom to another atom through this circuit of unhybridized p orbitals. So for these electrons to move, they have to go through sp2 centers, because if you have an sp2 center, then you have one unhybridized p orbital on that, in this case, carbon. So each one of these carbons has a hydrogen attached. So benzene is actually C6H6. Now, the electrons go from here to here to here to here. So this double-headed arrow just shows that they can move. And these structures are actually equivalent. The double-headed arrow means that they're actually the same thing. So for benzene, there's 2 resonance structures. And the more number of resonance structures, the more stable. and that can solve a lot of problems. Acetate. Acetate is, this is your acetyl group, and acetate is the ion. Okay, so the acetate ion. And basically you have, if you do the Lewis structure, which you're supposed to know how to do Lewis structures, remember oxygen likes 2 bonds and 2 lone pairs, and then an oxygen with a negative charge with 1 bond would have 3 lone pairs. Now, this carbon here is an sp2. This carbon here is sp3. And this oxygen is sp2. You see it has 1, 2, 3 things. Okay, so remember you count your superscripts here. The understood 1 is with the S and the 2 with P. So this is sp2. So the electrons can go from the oxygen to the nitrogen, and then the electrons in this pi bond can go up to the oxygen. And then if you were to draw the resonance arrow, you would do the double-headed arrow, and you would redraw this. Now all the sigma bonds stay the same, but the pi bonds have moved, and now you have 1 sigma bond to this oxygen, and its formal charge would be a negative, and you have still 2 lone pairs, so that oxygen would be neutral. And so acetate has resonance stability, and it has 2 structures. Okay, the next one, if you see this is, you see that's a carbon anion. Okay, so let's redraw this. Cyclohexanol, and then the negative charge here is right here. So if it's negative charge there, that means there's 2 electrons on that carbon. So this carbon has 2 electrons. Now, can it undergo resonance? Well, let's look for sp2 centers. This oxygen has 1, 2, 3, 4. So I'm going to say that oxygen is an sp3. 1, 2, 3, because there's no charge on it. These guys are methylene CH2s. Those are sp3. This is sp3. So is that a negative? If it had been a plus, let's say if it's a plus sign, just because what if it's actually drawn wrong? And if it is a carbocation, then these electrons could go back, and that would make a resonance structure, because that would have an unhybridized p orbital that could basically take on those electrons. So that could form a double bond with hydrogen, and then you would have a plus charge. You have to have conservation of charge. The only things that can move in resonance structures are the electrons in the unhybridized p orbitals. Okay, the next problem here is this compound here, and that is actually a positive, so that's a plus charge. So let's do this. CH3, which is sp3, the carbon is a plus, so there's 2 lone pairs, and then you have OCH3. Now, so you have these 2 electrons here. This is an sp2 center, and you can go from here to there. And then you redraw with your double-headed arrow. And it would be CH3. Keep your sigma bonds, double bond, CH3. This is going to be a plus charge now. because you got 3 bonds to oxygen with a lone pair, and now oxygen. Let's see if I can erase that. Draw that sigma bond, and then that's your resonance structure. It's just the movement of electrons. And then the last one is trifluoroacetate. So this last one here is trifluoroacetate. So there's 3 fluorines here. This is sp3. It's very electron negative, so it's pulling those electrons. And this acetate means it came from trifluoroacetic acid, which is pretty acidic. It means it wants to let go of that proton. So this is the result after it's been deprotonated. And when you're drawing the resonance structures, you want to draw your full Lewis structure with all your lone pairs. These electrons will go towards that sp2 center and then push the electrons up in that pi bond. So you get, let's draw this. Now you have a negative charge on this oxygen, and you keep the 2 lone pairs. And these are equivalent structures. And that's why it's stable. Okay, this is problem number 5. This is the structure of morphine. It's an addictive analgesic. Means painkiller. Is shown below. Enter the labels in the appropriate blanks. Okay, so we've talked about resonance structures and Lewis structures and pKa's and acid-base chemistry. Now, and we've talked about knowing your bonding patterns on page 13. Now we're going to talk about hybridization. This is chapter 2. So we're asking about hybridization and pi electrons and recognizing the acids. This once again is either primary, secondary, tertiary, or quaternary. And talks about functional groups. You need to know your functional groups. Functional groups are on page 72, and they're in chapter 2. That's section 2 through 13. I say learn your functional groups early, because the sooner you can recognize those functional groups, the sooner you can figure out the reactions. You need to classify these reactions. You need to be able to name them. It's the language. Okay, so type of hybridization. So the first one, and you know what's lost on here is this. So we're going to go down here, A, B, C, D, E, F, G, H. Okay. So type of hybridization for A, well, you got an alkene. So when you draw an alkene, you have this carbon is connected to 1, 2, 3 things, sp2. So you can just add your superscripts. So this is sp2, hybridization. B, type of hybridization. Okay, that's a nitrogen. Now, when you get structures like this, you don't see a lone pair. But notice you've got nitrogen connected to 3 bonds. What you don't see there is a lone pair. Okay, so what do you have? You have 1, 2, 3, 4. That would be sp3. So that is an sp3 hybridization for B. Okay, because it's connected to 4 things, and you can just add the superscripts there. How many pi electrons for C? So we find C. Well, it's a benzene ring, and each pi bond has 2 electrons. These pi bonds are here. So you have 1, 2 there, 3, 4, 5, 6. So you have 6 pi electrons. D, how many pi electrons? That's just an alkene. You have 2 electrons in those pi bonds there for D. This type of acid. Now, What does that mean? So E. This is a phenol acid. So if you had to look up its pKa, you could look it up. It's 10 pKa. So it's a phenolic acid. They're pretty acidic. F. What kind of acid is that? I would want to say an alcohol, but it's an allylic alcohol. And that is important because the so what you have here, I'll just redraw a portion of it. You have this double bond here. So this is an allylic alcohol. You've got to include this double bond because it's resonance stabilized, and that will make a difference in its pKa. Do I have the pKa of an allylic alcohol here? I would have to look that up. Okay, functional group. So G, functional group here would be an ether. So look at that and be able to recognize that that would be an ether. And then H, it's asking, so we're going to talk about alcohols. So that alcohol there, actually let's just look at here. That alcohol there for H is connected to a carbon that's connected to 2 other carbons. So this is called the carbonyl carbon. And the carbonyl carbon is the carbon connected to the hydroxyl group. And that carbon is connected to 2 carbons, which makes that a secondary. Okay, in this problem it says, consider acetylene, chloroacetic acid, ethane, and ethanol in answering the following. Okay, well, what's acetylene? Acetylene is your carbon-carbon triple bond. Chloroacetic acid is chloro. So we know what a chloro is. Acetic acid, that's 2 carbons. So this is acetic acid, and this carbon obviously needs 2 hydrogens. So that's chloroacetic acid. Ethane. Well, ethane is CH3, and ethanol, CH3, CH2OH. Now, I like to think about the pKa's, because it's talking about arranging these compounds in the order of increasing or decreasing pKa. So if you haven't noticed already, pKa's and acid-base chemistry is important in chemistry. There's a pKa table on page 25, and then there's also another one on page 393, which might be even better. When you look at these pKa's, this is about a 25. Is that right? Yes. So that's acetylene's got a pKa of 25. Acetic acid is around 4.74. So let's just write 4.7 for chloroacetic acid. Ethane has a pKa about 50. And then we have ethanol, and that's about a pKa of 16. So arrange these compounds in order of increasing or decreasing pKa. So basically your most acidic is chloroacetic acid. So chloroacetic acid. And that's less than the next one, which is ethanol, which is less than acetylene, which is less than ethane, which is just your carbon. Write a balanced reaction in which ethanol is an acid. So the ethanol has to be an acid. Now you're going to have to do a little thinking here. If ethanol is going to be your acid, then that means it has to be deprotonated. So it has to have a stronger, it's got to be deprotonated by a stronger base. So I just used, if you deprotonate this acetylene, so I'm just drawing my equilibrium, and then what would happen here is this acetylene, you could put a sodium plus in there if you want, would deprotonate and generate the ethoxide. But I tell you what a better one would be, something that would actually happen. Let's do this. Okay. How would you generate, if you put sodium metal, you actually generate this sodium ethoxide. And that's how you actually generate it. You put the sodium metal in there, and then this gives off 1/2 H2 gas. So that's how you would generate it. pKa's here. You're looking at the pKa of, you gotta look for your proton there, is 16 for ethanol. And if I look on page 25, see if I can see if they have hydrogen gas on there. What is the pKa of hydrogen gas? Do you all see hydrogen gas? Sometimes you have them. Not real sure. But if you could look at that, I guarantee you it's going to be lower. So I think I might take a break and look that up real quick. Alright, well, I looked up the pKa of the hydrogen, and the pKa of the hydrogen is 35. So what did I say? Yes, so the equilibrium lies towards the sodium ethoxide. Okay, the next question says, write a balanced reaction in which chloroacetic acid is a base. So chloroacetic acid. Chloroacetic acid is the base. Chloroacetic acid would need to, if it's going to act as a base, then it's going to have to react with a stronger acid, H2SO4. Okay, so in such a situation like this, the carbonyl would get protonated. And you would get HSO4 minus. Now, let's look at the pKa values. So pKa value of the chloroacetic acid is 4.75, and the pKa of HSO4 is -10. Yeah, this isn't, I'm going to say this isn't happening. So, and when would it act as a base? Okay, so even though I'm going through some of these reviews, we're just going to scratch that there. Okay, write a balanced acid-base reaction in which ethane is formed as a product. Okay, so this is a classic reaction, and you need to know this, the Grignard reactions. A Grignard reaction would be like CH3, CH2, magnesium bromide. Okay, now if this reacts with water, even 1 drop of water, you're going to get protonation. So basically this is a delta positive, this is a delta negative. This is kind of nice because the carbon is a negative, which is usually a positive, so that's called an umpalong. I like that word, umpalong. I think it's umpalong. It's a German word. Anyway, CH3, and then you get magnesium bromide and OH minus. Now, if you look at the pKa values of water, which is 15.7 pKa of water, and you compare that with ethane, pKa of 50. So it definitely goes towards the higher pKa value. The equilibrium goes towards the higher pKa value, which is your weaker acid. Okay, this question. When R3-methyl-1-pentene-3-ol is reduced with palladium and carbon under an atmosphere of hydrogen, the resulting compound is, and this word is inverted, non-chiral, racemized, or unchanged. Now, this is a good review question because it brings in your stereochemistry and your functional groups. Naming is important. Now, your exams aren't going to necessarily be tested on naming, but you have to understand the names. So, pentene is 5 carbons. So let's draw the structure, 1, 2, 3, 4, 5. If you're in a math class, you'd have to solve problems using the calculator. But you're in organic chemistry, you solve problems by drawing, okay? So we draw. Pentene, that's 5 carbons. On the 3, you have the OL. So 1, 2, 3, 4, 5. So on the third carbon, we have an OL. Let's go ahead and draw in the O. The OL means alcohol. Okay, so you have the alcohol on the third carbon. And then you have the ene, pentene. See the E and E? That's on carbon number 1. Okay, and then on number 3, you have a methyl. So we're just going to go ahead and draw in a methyl on the 3. Now, do you remember how to name? So you do the higher priority. These are the con-pre-log naming system, and your higher priority, it depends on your atomic number. So you're comparing oxygen, a carbon, and a carbon. So the oxygen would be 1 because it has a higher priority because its atomic number is actually 6. Carbon is 4. Now, what I like to do when I have like 3 carbons, and they tell you how to do this in the naming of compounds, but I like to do it is, this is a methyl, CH3, or we're comparing a methylene, CH2, that's a CH2 methylene, and then this is a methine. So these are methine, this is a methylene, and this is a methyl. So obviously the methine is going to have a higher priority, so we're going to call that a 2 because it has more carbons and stuff connected. Methylene is 3, and then the methyl is 4. So if the 4 is in the back, we haven't drawn in our wedges or dash, but the 4 is in the back, your lowest priority, and this is rotating clockwise. Clockwise is R. So we want the R and we want the methyl in the back. So then we can just go ahead and draw your dashes and your wedges. And so the question, so you have to draw the structure. with its stereochemistry because it's giving you stereochemistry with the R. It is reduced. So here we're talking about reduced with palladium on carbon under an atmosphere of hydrogen. So hydrogen gas. This is called, you got to recognize what it's called. That's a hydrogenation reaction. And this is hydrogenation of alkenes. This is chapter 8. So this is review on chapter 8. So the hydrogen is going to add what functional group? The alkene, the carbon-carbon double bond. And what does it do? It reduces it to an alkane. So if you remember correctly, the palladium metal gets absorbed, the hydrogen gets absorbed on the palladium metal. Otherwise, the hydrogen bond does not break. And then you have your alkene that comes along, and it kind of hovers over the hydrogen, and then the hydrogen adds to the alkene on the same side to make an alkane. So when you draw the structure, you just draw the alkane. And what I like to do too is I like to name them when I get done. So 1, 2, 3, 4, 5. This adds another level of detail so we know that we are doing the right reaction. So in this case, this would still be R3 methyl pentane 3-ol. Okay, so now the ene went to the ane, and you did not even touch the stereochemistry. The stereochemistry stays the same. So it's not inverted. Okay, that's an SN2. It's still chiral because it's an R. It's not racemized because you didn't even touch the stereocenter. The answer is it's but it's not really unchanged, is it? So in this, I think that's not necessarily a good question. It's not inverted. Actually, no, it is. That's funny. This is a good question. Do you realize that this is no longer chiral? The answer is non-chiral. Because look at this. The ethyl group, both ethyl groups. So now you do not have an asymmetric carbon. So you don't even have to draw with a wedge. So it's just 3-methyl pentane 3-ol. It is asymmetric. It's achiral. That was a good question. This question is cis-2-cyclopentane 1,4-diol exists as how many pairs of enantiomers? So let's draw cyclopentane. That's a 5-membered ring. 1,4-diol. And it's cis, so that means they're on the same side. So we'll just draw, well, let's just do 1, 2, 3, 4, 5. So let's go ahead. And then 2 tells you, because it's closer to the cyclopentane. And then 1 is, we can draw this on the same side, coming at us, OH. 1, 2, 3, and 4 is OH. So these are on the same side. Another way to draw that, because it's flat, is to draw these down, OH, these up. 1, 2, 3, 4, that down, and that one up. Okay, because they're on the same side. How many pairs of enantiomers? So here, if you were to draw the cis, it has a plane of symmetry. So where's the plane of symmetry? So are these asymmetric carbons even? They could be, yeah. And so do you have a plane of symmetry? Yeah, so I think the best way is to draw it like this. And you might be able to see more of a plane of symmetry here. So if you were to draw its mirror image, because it asks how many enantiomers, this is its mirror image. And then if you were to see, you would see that's superimposable. So your plane of symmetry, which is how they do that with the sigma, has a plane of symmetry. So the answer is 0 enantiomers. These are the same compound. And that means they're achiral, if it has a plane of symmetry. They also call this meso. Okay, when S1-bromo-3-phenylbutane is treated with zinc acetic acid, is the product racemized? Well, let's draw our compound. So we have butane. So 1, 2, 3, 4. And 1 we have bromo, 2, 3, and then we'll just draw this in and see if it's right. That's phenyl. Phenyl is a benzene ring. That's a substituent. And we have, so on the 1, 2, 3 phenyl, 1 bromo. Now let's see. So when you apply your RS nomenclature, what are you comparing? You're comparing a hydrogen, you're comparing a carbon, you're comparing a methyl group, which is number 4, and you're comparing a methylene group, which is number 2. So the priority would be the 1 carbon would be the highest, because it's going to be connected to more carbons. The second will be your methylene, so let's just go 1, and then methylene, that would be 2, and then the third would be your methyl. And so if you did this, you'd say that is clockwise R, but your hydrogen is in front, so you'd have to do the switch, and this would be S, and that's what you're wanting, and we happen to draw it correctly. Now the question is, what if you treat this with zinc and acetic acid? Okay, so that's acetic acid, sometimes used as a solvent. Is the product racemized? Well, what's zinc going to do? Zinc is going to insert kind of like a Grignard reaction, and the acetic acid is going to quench it. So basically, it's going to reduce your alkyl halide to an alkane. So you're going to go from an alkyl halide to an alkane. So then when you draw this, you draw 1, 2, 3, draw your phenyl and your hydrogen here. 1, 2, 3, 4. So all you did was reduce off the bromine here. So is it racemized? No, it didn't even touch this carbon 3, and that's your asymmetric center. So no, it's still the same. It's still going to be S. Okay, what about when R1-iodo-3 phenylbutane is treated with 1 equivalent of lithium dimethyl cuprate? So let's draw this structure. Okay, so when you draw that structure, you should get something that looks like this. And let's check it. So we have 1, 2, 3, 4. That's butane. 3 phenyl. 1 iodo. And then let's see if we get the R right. So we're dealing with a carbon. It's the same. That's 1, 2, 3. So when you go like that, you see that that's R. Hydrogen's in back, so you keep it as R. So that's correct. Now if you react this with dimethyl cuprate, so that's dimethyl cuprate, basically what's going to happen is it's going to do an SN2. So your copper is delta positive, which makes one of these methyls a delta negative, and it does an SN2. You have a primary alkyl halide, and the iodo group is an excellent leaving group. So then you redraw this, and what you have is a extra methyl, this methyl group here. So 1, 2, 3, 4, 5. You now have a pentane instead of a butane. Notice you did not do any kind of chemistry on this asymmetric center. So it's still asymmetric. It's still going to be R. And it would be inverted. So because it's an SN2. So they're looking for, this would be inverted. But it's just kind of a tough question, because are you talking about the stereocenter, or are you talking about the fact that you recognize this as an SN2 reaction? So I try to stay away from questions that are tricky like that on the exam, but for review purposes, I think it's good. It teaches you how to draw the structures, practice your naming, and then it asks for a reaction like lithium dimethyl cuprate. So as a review, that's a good question. Given the following carbonium ions, which has the highest order of stability? So carbonium ion. This is chapter 6. And you need to look at your stability of carbocations. Which one has the highest order stability? And what is your stability of carbocations? Tertiary is more stable than secondary, which is more stable than primary, which is about as stable as a methyl. Okay, that's a primary. So I think I even wrote out the answer for you. So 2-methyl, 2-propyl. So 1, 2, 3. So you can see that this one is 2-methyl, 2-propyl. Ethyl is this compound right here. That's ethyl, and it's primary. 1-propyl is this compound here, and then this is 2-propyl. Okay, the diagram shown represents what? So what's going on here? This is a transition state, and in this transition state, what's happening here? Do you recognize this is a leaving group? And this is a nucleophile. And you have backside attack. So that would be an SN2 transition state. And E2 would be taking a hydrogen away. So if you have your leaving group here, and E2 would do something like this. You would see the base, and it would be taking the hydrogen away, and then these electrons go here, and the leaving group goes there. So your transition state would look where I've drawn those arrows. You would draw a transition state such as this. So you would keep all your sigma bonds. So any bond that gets broken would get a dot. So this would be a dot here, this would be a dot there, This would be a dot there. This would be a dot there. So that would be more of a transition state for an E2. Halogenation is the same thing as an E2 elimination. In the transition state of retention reaction, the retention reaction would be what you get with a carbocation. So in a carbocation, this would be flat. And your nucleophile with its lone pair could either come from the top or it can come from the bottom, but it's coming, and that would be a retention reaction if it came from one phase. Which of the following structures represent enantiomers? So this is still dealing with your stereochemistry, your chapter in chapter 5. These have cis, so these have a plane of symmetry, and this would have a plane of symmetry. So now these two do not, and then you could name them, and if you start with this one, you would get an S, and that would be R, and then this would be R and S. So that would be, and you could do oxygen is 1, then this would be 2, 3, so you see that's R, but the hydrogen's coming at you, so then you go in back and it would be S, and you do that with the same. So these two would be enantiomers. There's no plane of symmetry. The cis on the cis rings typically have planes of symmetry. The Williamson ether synthesis utilize an alkyl halide as an electrophile and blank as a nucleophile. So this reaction is an SN2 reaction. It's on page 271 and 497. So the Williamson ether synthesis, if you look it up, you'll see that it makes an ether. Surprise! Ether. And so you take an alcohol plus the sodium. We did this earlier and we made an alkoxide, which is a very strong base, used a lot, and then you actually get about a half of hydrogen gas. Okay, and the hydrogen's coming from the alcohol. So it's an acid-base reaction, and then once you get an alkoxide, the alkoxide is your nucleophile. So which one is it? There's your alkoxide, it's a nucleophile. You react this with an alkyl halide, and it has to be a primary alkyl halide. So if you react this like with methyl iodide, then what happens is this does an SN2 reaction, and you get ROCH3. This R could be any kind of alkyl group, so it could be ethyl, which is CH3, CH2. In that case, this would be CH3, CH2, OCH3, and that would be ethyl methyl ether. So you learn how to name these and you learn to recognize the reactions. It makes it a little bit easier because you kind of have a path and you know where you're going. Okay, which of the following halides is the most reactive in an SN2 reaction? Well, you need to know a little bit about the SN2 reactivity. So I would look at page 215, and it talks about alkyl halides for SN2 reaction. So alkyl halides are such as CH3 iodide, iodomethane. Now this would be a methyl. And then you could have ethyl, CH3CH2 iodide. And if you look at this carbon that's connected to the iodide, it's connected to another carbon. So that's a primary. And then if you have like an isopropyl iodide, so that carbon is connected to two other carbons, so that would be a secondary. And the methyl are more reactive than the primary, which are more reactive than the secondary. Tertiaries, alkyl halides, do not react. Now, if you notice the carbon that's connected to the leaving group, in this case iodide, each one of these are sp3 hybridized. That's important. So for these substrates, you need an sp3 hybridized carbon to the leaving group. So let's draw these out. That's how you solve these problems. Trans 1-chloropropene. Propene has 3 carbons, and you've got your ene is the carbon-carbon double bond. You have on 1, you have the chloro, 1, 2, 3. And it's trans. In that case, I have drawn it as cis. So let's redraw. Chloro, trans. Okay, so that would be your compound there. That's not going to go in SN2. Do you know why? That carbon is connected to that chlorine, and that's an sp2. So what you don't see here is a hydrogen. So it's got 1, 2, 3 things connected to it, so that's sp2. So they do not undergo SN2. Okay, so the next one is cis 1-chloropropene, which is what I drew here. And once again, that's an sp2 carbon. Okay, it has to be an sp3 carbon. The next one is 3-chloropropene. So if you have propene at 1, 2, and then this is a chloro. Now this is actually very reactive. That carbon there has 2 hydrogens on it. It's a methylene. So that would be an sp3 carbon. And this is not just, this is not like your typical primary, because it has a carbon-carbon double bond, 1 carbon away. So this is an allylic primary, allylic alkyl halide. And then the next is 2-chloropropene. So this would be 2-chloropropene, and once again that carbon is connected to an sp2 carbon, that chlorine. So that's not going to undergo an SN2. So which of the following halides is the most reactive in SN2? It'd be the 3-chloropropene. Okay, the formation of 1-methyl-cyclopentene by adding 1-methyl-1-cyclopentanol to a mixture of concentrated hydrochloric acid zinc chloride is an example of a blank reaction. Alright, well, I don't know about you, but I kind of have to draw these out. So, cyclopentene, and so 1-methyl cyclopentene, 1-methyl-cyclopentene formation. So that's your product. So let's draw the arrow this way. By adding 1-methyl, 1-cyclopentanol. Okay, so you have an alcohol. And you're going to add zinc chloride and acetic and hydrochloric acid, HCl. So these are very strong dehydrating. This is a dehydrating acid. And you have an alcohol. So what happens is it's going to get protonated by your HCl. going to get protonated, and then when it gets protonated, it's going to turn into a good leaving group, water, OH2 plus. And so this is going to leave. And because you're under acid conditions, you're going to form your carbocation. This is a tertiary carbocation. You always classify them when you form a carbocation. And so then what happens? It's showing you right here you formed a double bond. So you can take a hydrogen, doesn't matter if it comes from this carbon or this adjacent carbon. It's not coming from here because that would give us a less substituted, and so then what happens is you lose this hydrogen, and it forms the product. And so that would be an E1 reaction. The reaction of potassium terbutoxide. Potassium terbutoxide. It's a strong hindered base, okay? See how you classify everything? It's a strong hindered base with trans 2-methyl-1-bromo cyclohexane. Okay, so let's draw this out. 1 bromo, 2 methyl, and it's trans. So one of these is going to get a dash, and the other one's going to get a wedge. Okay, so if you look, all these products are elimination, and which makes sense because you're using a strong base. But now when you're dealing with cyclohexanes, you have to draw the chair out, okay, because we're dealing with a strong hindered base. We're dealing with an E2 reaction because we're also dealing with a secondary alkyl halide. So you got to recognize what you're dealing with here. Strong base, and it's a hindered base. So you're actually going to get and it's E2. So E2 is going to be what? It's going to be stereospecific. So if you study your review, you'll see that the E2 mechanism is on page 262, and you have to abstract a proton, and it prefers to be anti-coplanar. So let's draw this. We want the bromine to be equatorial position. So you remember this is axial and this would be equatorial. Now if that is up, you see that's equatorial up, then the other one has to be, the methyl has to be down to make that trans, because it says trans here. So that's equatorial down. Now, in order for bromine to be in the leaving group position, we need to have it in the axial position. So what we're going to do is we're going to do the ring flip. Now, if you remember when the ring flips, what's equatorial becomes axial, and so if these are trans, this is down, this is your methyl here, and then that would be down. So they're still trans, so you just check it. The methyl is up and the bromine is down, and now they're both axial because they're both equatorial, so now they go to axial. But you notice that you're going to have to abstract a hydrogen either from this carbon or from this carbon. And this carbon, the hydrogen, is not coplanar with the leaving group. So then you basically go to the next. As you can see, what you don't have drawn in here is axial and equatorial hydrogens. So your base is going to come here. It's going to take this proton and kick that as your leaving group. And then to redraw this, basically you get the double bond here and your methyl stays up. And so then when you want to draw this flat, you got 1, 2, 3, 1, 2, 3. And so now it doesn't matter whether it's up or down. So that would be your answer. Using dimethylformamide, a lot of times you'll see that as DMF, dimethylformamide or formamide. I've heard people, it's like creek or crick. As a solvent, and 1-iodobutane, 1, 2, 3, 4. So 1, 2, 3, 4. 1-iodobutane is an electrophile. Which of the following is the least nucleophilic for SN2 reaction? So you're looking for a nucleophile that is less reactive. Now this brings you to studying page 233, section 610, chapter 6, section 10. And it talks about methoxide would be more nucleophilic than methanol. It's like 1,000,000 times more nucleophilic because you have a lone pair and negative charge. So here you have sodium azide. That's a negative charge. That's an excellent nucleophile. Okay, we're looking for the least. Ammonium chloride. Okay, that's actually your answer. So when you study these and you see that, you'll see that chloride is just okay. It's okay. Diethylamine is considered pretty strong. Diethylamine. It's in the strong column when you look at that the table. And sodium cyanide is strong. You get a carbon with a negative charge. So that's a strong nucleophile. Cis-1,4 dichlorocyclohexane exists as how many pairs of enantiomers? And we're going to skip this for now. For this problem, this is page 191, and it is section 5.9, and it's about chiral compounds without asymmetric atoms. And in this, actually, I'm going to say, no, it's 189. 189, 5-8. And it's the chirality of conformationally mobile systems. And so when we have a cyclohexane, and we think about the chair conformation, and we draw in the cis and trans, equatorial, axial, and then we try to decide whether that has enantiomers or not, or chiral centers. The thing is, a molecule cannot be optically active if its chiral conformations are in equilibrium with the mirror images. So we consider such a molecule to be achiral, and there's an example. So basically, what this is telling you is that you can draw this molecule flat. So, and then you look for a plane of symmetry. So here we have cis 1,4 dichloro cyclohexane. So 1, 2, 3, 4. And another way to draw that would be, you can draw below 1, 2, 3, 4. And at this point, you can see a plane of symmetry. And so if there's a plane of symmetry, then it would have 0 in enantiomers. Okay, which of the following is formed when 1,2-dimethyl-cyclohexene is treated with deuterium gas in the presence of a platinum catalyst? So this is deuterium gas, which is D2. And D2 is a way to label the carbons. And so this is a catalytic hydrogenation reaction. D2 can act like H2 and chemically. And so the starting material is 1,2-dimethyl-cyclohexene. And so that is the compound drawn here. And when you react that with platinum and hydrogen gas, you get the deuterium, and the deuterium is going to add on the same side. So it adds cis here. As you can see, I've drawn these coming up, and then the methyl is going back. And if I look at these 4 compounds, the first compound is the correct answer. Problem number 21. So we have 2,3-dimethylcyclohexane may be prepared. So this is a product. So we have 1, 2, 3, 4, 5, 6, 2, 3 dimethylhexane may be prepared from 2,3-dimethyl-1-bromobutane. So we got 1, 2, 3, 4. And on the 1, we have bromo. So we'll call that carbon number 1. And then on 2, we have CH3. And then on 3, we have CH3. Now let's look at the difference between the molecules here. So this carbon would be this carbon. This methyl would be that methyl. This carbon would be that carbon. And then this number 1 carbon, we'll put a star there, is this carbon here. So what have we done? We've essentially added 2 carbon fragment. And when we look at these, we see here, this is called the Gilman reaction. I don't think we've gone over this yet, and I'm not sure. Sometimes it's introduced in your SN2 chemistry with the Grignard, but we will be going over it, so we'll just go ahead and throw it in there. I want to give you the information here. Yes, it is called Gilman reagent. And Grignards are really bad about reacting with alkyl halides. But this lithium dialkyl cuprate is very good. And so you can make carbon-carbon bonds with it. And so basically what you have here is CH2, CH3, and there's 2 of them with a copper lithium. And this is going to get this carbon a positive. Wait, sorry, that's wrong. Okay, so the metal is electropositive, so it becomes like a positive charge, and here the carbon is a negative charge. And so this negative charge is attracted to the delta positive carbon that's connected to the halogen here, which is delta negative. So this is your dipole, and this is kind of the electrostatics that drives this reaction. And we call this, of course, the electrophile, which I just write E+, and this is your nucleophile. Okay, so what happens is the electrons from this carbon attack an SN2. This is SN2 reaction. The carbon that's connected to bonded to the halogen, and then your halogen Br is your leaving group. This is a backside attack, and now all you're doing is adding this ethyl group. So then your compound is the product you were this is CH2, CH3. So now you can do 1, 2, 3, 4, 5, 6. It's always good to count, make sure 1, 2, 3, 4, 5, 6. And that is the answer. Okay, this problem is methyl tert butyl ether. So what does that look like? Methyl tert butyl ether may be made from which of the following compounds by an SN1 pathway. So we're dealing with Chapter 6 review, SN1 pathway. So this is your methyl tert butyl ether. And an SN1 pathway, you need to have, it needs to be acidic. Okay, so you don't want a base. So let me just tell you right now, SN1, you don't want a strong base. Potassium tert butoxide, yeah, that's a strong base, so you don't want that. Terbutyl chloride, okay, that's good. Terbutyl chloride, what happens here? It's a tertiary alkyl halide. That's good for SN1, right? And then that's going to give you a tertiary carbocation. And then, how do you get this portion? Well, I guess that's not actually an option here. Let's see, and what's the other one? 2-methyl 2-iodopropane. So what does that look like? There's propane. There's 2-iodo, and then 2-methyl. Okay, and then the iodine's the leaving group, which would give you the tertiary carbocation. And so this would also work by an SN1 pathway. Okay, E2 reaction of RS. What's that mean when you see RS? When you see RS like that, it means it's racemic. Sometimes when you purchase chemicals, if they RS, that means half of it's the R configuration, the other half is the S. So 2-bromobutane would be 1, 2, 3, 4, and then 2 is the bromo here. As you can see, that's your asymmetric carbon, because what's connected? You have the bromine, you have a hydrogen, you have a methyl group, and an ethyl group. And so then the other one would be where the hydrogen's coming at you and the bromine. And so just for fun, we'll go ahead and do this. 1, 2, 3. So that would be the hydrogens in the back counterclockwise. So that's your S enantiomer. And then this would be 1, 2, 3. But even though it's counterclockwise, your hydrogen is in front, so you got to do the backward rule. So that would be an R. So those are your two, and you have both of them. Now E2, this is chapter 6, reaction with sodium ethoxide. So what does sodium ethoxide look like? Sodium ethoxide and ethanol, and that's typical. You take ethanol and you throw it in with some sodium metal, stir it up, and that'll make sodium ethoxide, which is a strong base. You need a strong base for E2 reaction. And now let's look at what that's going to give us. So I'm just going to go ahead and draw this molecule without the stereocenter. And you've got a hydrogen here. You look at when you're doing the elimination reaction, you look at the carbons adjacent to the carbon that's covalently bonded to the leaving group. So you have the hydrogens here on we'll call that on the number 3 carbon, and then you have the hydrogens on the number 1 carbon. And so your sodium ethoxide base is going to take one of these hydrogens away. Now, there is a rule. It's called Yatsev's rule. And if you remember, go back and review what Yatsev's rule is. It's going to make the most stable alkene. And so unless the other rule would be Hoffman product. The Hoffman product, you have to have a very sterically hindered base. So if you see tert butoxide as your base, like potassium tert butoxide, or LDA, lithium diisopropylamide, those are bulky bases. And when you're doing an E2 elimination with those bases, you need to start thinking Hoffman. But sodium ethoxide is a small base, so you need to be thinking Yatsev's, and that means you're going to get the most stable alkene. So which proton gets abstracted that's going to give you the most stable alkene? Yes, it's going to be the number 3 carbon proton. So basically what happens here is this base will abstract this hydrogen, and this is a concerted reaction, meaning one step, it's all going to happen. Remember, it's stereospecific, which most of your concerted reactions are. So this is going to have to be anti-periplanar. That means they're going to be in the same plane. We don't have to really worry about this here because it's not conformationally restrained. But what you get here is, let's count carbons. 1, 2, 3, 4. Always check, count your carbons. And that is your product. So, what's our options? 1-butene? No, 1-butene would give you something like the Hoffman product. R2-butanol? No, you're not. You're doing an E2 reaction, so you're going to get an alkene. Trans? Yes, trans-2-butene. See, 1, 2. This would be trans-2-butene. And the other one is a ethyl sec-butyl ether. No, you're not getting an ether. This review question, number 24, write the structures of the products formed when 8-bromo-2,6-dimethyl-2-octene is reacted with the following. Okay, so here is your Gilman reagent again. The alkyl, actually it's the dialkyl lithium cuprate. And let's go ahead and draw our substrate. So what's our substrate? Octene. So I'm going to draw 8. 1, 2, 5. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to go ahead and number 1, 2, 3, 4, 5, 6, 7, 8. Okay, so there we have our 8. And the 2 means the octene is right here. That's your double bond on the 2 carbon. And 2,6-dimethyl. So we'll put a methyl on the 2. And then we're going to come over here on the 6 carbon and put a methyl. And then 8-bromo. So we're going to put a bromo here. Okay, so what functional groups do you have in this molecule? You need to always kind of look for acidic protons. Look for functional groups. Yes, you have an alkene between carbons 2 and 3. You have an alkyl halide. And that is in carbon number 8. Okay, so we have a cuprate reagent, and that makes carbon-carbon bonds with alkyl halides. So let's draw that. It's basically a CH3, CH2, copper, lithium. It's an ether. So if you remember, the copper is positive. This makes a negative carbon. It's going to go after the delta positive carbon. And this is an SN2 reaction. And so basically now you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you draw in your CH3, keep your alkene, 2, 3, 4, 5, 6, get your methyl. Don't forget to put all your other substituents. And I like to name these after I draw them. So in this case, if it's good practice, you should too. So that is decane, but it's decene, and that's on carbon number 2. And you still have the 2, 6 dimethyl. Alright, so what happens if you take this molecule and you react it with catalytic hydrogenation? So this is chapter 8, catalytic hydrogenation. And you're basically going to reduce that bond, and you're going to do it in a syn fashion. So you're going to 1, 2, 3, 4, 5, 6, 7, 8. And you're going to basically add hydrogen and make the alkane. And that still has a bromine. So that's your product. Okay, the next reaction, sodium ethoxide and ethanol. So when you react this with sodium ethoxide, that is a strong base, and it's a strong nucleophile. This is chapter 6. So this, you have to look at your substrate, and you have a primary alkyl halide. So because it's primary and it's not secondary, it's more than likely going to do an elimination faster. Not elimination, substitution faster than it's going to do eliminations. So 1, 2, 3, 4, 5, 6, 7, carbon number 8, and basically this nucleophile is going to come in backside attack SN2 and displace the bromine to make OCH2 CH3, and this is an ether. So you need to kind of look at those functional groups and see that that's an ether. And the last one is sodium cyanide and DMSO. So sodium cyanide, that's a strong nucleophile. 1, 2, 3, 4, 5, 6, 7, 8. And you're going to have the cyanide do a SN2 backside attack. Your bromine's going to be a leaving group. And that's carbon number 2, 3, 4, 5, 6, 7, 8. And then 8 you have the cyanide CN. That's your new bond right there. Okay, using Newman projections. Newman projections are chapter 3, page 99. And also on page 101, you can see that you have anti-staggered. So staggered, when you want the lowest energy, if you remember, that's going to be staggered, and it's going to be anti, compared to, remember, gauche. So to draw ethane, so ethane is CH3, CH3. And So let's make one of these blue carbon and one of them red. Okay, so if you had your eye here and you're looking down this bond, this is what you supposedly would see. And I just always draw them like this. Kind of draw that first. And then in the back, I draw a circle. The circle is the blue carbon. And then you draw the 3 there. And that would be these 3 here. So coming off of the back carbon, you see where it's connected to the blue circle. And then coming off of the red carbon, you have the hydrogens here. And what you're looking at is it's called the dihedral angle, and here it's 180 degrees, and that would be anti. And ethane's not that big of a deal because it's just 2 carbons and they're all hydrogens. But like you get into butane. So now when you get into butane, you have different conformations because you get rotation around the single bond. And so what's this look like? So let's look at this bond. We'll still keep the same red in the front and blue in the back. So your eye looks here. When you look here, we'll draw this front, and you still draw the same. You draw this like little Y thing, and then the back you draw the circle. And then you draw this, because this is your most stable conformation. So you can just draw that, and then you can figure out what you're going to put on it. So here, you're going to have a methyl group. Now this is what's important. You want the lowest energy. So let's put one of the methyls up here, and then put the hydrogens on the other ones. And then here, you put the methyl down there, and then the hydrogens, because you got the hydrogens here. So basically this is an anti, and your dihedral angle is 180. Okay, the next one's a cyclohexane. A little more challenging, right? And the way you do a cyclohexane is we're going to draw this as your red, and then this would be your blue. Now the nice thing about this is they pretty much all have hydrogens, right? So this has hydrogen and a hydrogen. This has a hydrogen and a hydrogen. So the way you draw that, and it's good to practice that, you're going to draw that carbon there, and then this one's going to be that one back there, and then this one will also be that one back there. So now what we're going to do is we're going to draw the same thing we always do, and then we draw this in the back, the circle, which is this one right here. And now this one here, see how it goes down? This is going to go down CH2, because that's that CH2. Put a star by it. And then this one, put a triangle by that one, is going up. There's your CH2. Now the rest is hydrogens connected to that. And then we come over here, and we're going to draw another one here. And just draw your Y, and then draw your circle, and draw your Y, and then you connect those. And it doesn't have to be perfect, but this is how you would draw a Newman projection of a cyclohexane ring. So that's just good practice to remind you of Newman projections. Okay, so this problem, answer the following by writing the structures of the significant organic product. And notice 1 equivalent equals 1 equivalent, 1 EQ. Now, so when you're solving these problems, you need to look at what's the functional group. And here, this is, the first one is an allylic bromide. So these are under the alkyl bromide or alkyl halide functional groups. So you define what functional group, and so you remember alkyl halides is the primary allylic bromide. So the allylic is resonance stabilized because of this carbon-carbon double bond. And then you see that you have sodium methoxide. So sodium methoxide and methanol and heat. So because this is a primary and it's a allylic bromide, which is even more reactive, this is a kinetic thing, this is going to be an SN2. This is going to be so fast. It's going to do backside attack, and then your bromide will be your leaving group. So this is your nucleophile, the sodium methoxide, and then it attacks your electrophile, which is your alkyl halide. And then that product is, so this is this carbon, and you're going to form a bond to the oxygen. That's your new bond, CH3. And that functional group is an ether. You see it's an oxygen connected to carbon. Remember, oxygen likes 2 bonds and 2 lone pairs. So now you have an allylic ether. The next problem. This, it kind of looks like tert butoxide, but it's not. So what is it? See, it has that carbon there. So that is a base. This is actually neopentyl oxide. So 1, 2, 3, 4, 5. And the book does talk about neopentyl. It's very hindered. And what's it doing here? You have, and I don't know if you all went over these. I think you did. This is a triflate. So what does this look like? This is trifluorosulfonic acid. Trifluorosulfonic acid. And so basically this is an excellent leaving group. Excellent leaving group. And so when you look at the leaving groups for SN2, you'll see that now this is hindered. So what's going to happen here is it will form an SN2. I think because that's such a great leaving group and that's a primary. So this is your nucleophile and that's a primary. And there's no way to make an elimination product with a methyl. So I think it's going to go ahead and methylate. So I think your product is going to be this neopentyl methyl ether. And that's your CH3 there. Okay, so the next one is you have 2 sites. You see that? You have 2 alkyl halides, and you have 1 equivalent of sodium iodide and acetone. Now, 1 equivalent. So you've got to look at both of these alkyl halide carbons, and let's classify them. So this one is a secondary, and this one is a primary. And you have 1 equivalent of sodium iodide. Iodide is an excellent, very polarizable, great nucleophile. So now you have 1 equivalent. Which one's going to happen first? That's right, the primary is going to happen first. So that's your nucleophile, and the chloride is going to leave. And then you're going to get SN2. This is going to be SN2, and count carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So the chlorine is replaced with an iodide. Okay, the next reaction is a dibromo compound, and you've got potassium tert-butoxide. This is a very hindered base. It's in T-butanol, and let me redraw this. So you have this cis dibromo, 1,2-dibromo cyclohexane. Now, this is secondary, and there's two of them, and let's make sure there wasn't one equivalent. It does say one equivalent, so we're only going to do this one time. So let's draw this. When you deal with the cyclohexanes, you need to draw the chair conformation, and you're dealing with, this is definitely an elimination. It's a strong base, so it can't be E1, and you're dealing with E2 because it's in a hindered base. So it's going to get the most accessible proton, but because it's E2, it's also going to be stereospecific, so it can only get the anti-coplanar proton. It's the only way it can abstract. So let's draw this. Now we know that the bromine has to be equatorial, and so then here this is down. So you draw the axial up, the bromine down. In this case, the bromine has to be down here. And the reason why that bromine has to be down is because it's on the same side. See, this is cis, and these have to be on the same side of the ring, which are both down. So one's going to be equatorial, the other one's going to be axial. Now, you look at the accessible protons. This bromine's not going to be your leaving group because it's not in the axial. So it has to be the diaxial. So you got to draw this in the diaxial. So this proton can be taken, or this proton can be taken. And so the base can abstract either one of these protons. And if it abstracts this proton, and then this is your leaving group, you end up getting, and we'll just draw it flat now, that is your product. And you lose your stereochemistry there. So that is actually a vinyl bromide. You see that's a vinyl bromide? It's very important to learn your functional groups, because if you can recognize your functional groups, you can really have a greater understanding of what's going on. Okay, and the last one is a tertiary alkyl halide, you see, and you have a very strong hindered base. Okay, so this is an excellent substrate for E2. So if you go back to chapter 6, you'll see that your tertiary substrates with a strong base, they're like the best for E2. And so what's going to happen here, let's just draw this over here, you're going to abstract a proton from one of these neighboring carbons. And they're all equivalent, so we'll just draw in one. And then your T-butoxide will go and take that proton, and chlorine will leave, and then you will get this compound here. And what is that? That is 1, 2, 3. That's 2-methyl propene. 2-methylpropene. Okay, the next question. Complete the following mechanisms by filling the boxes with appropriate structures. So this is good because you might see something like this on the exam, and you need, when I tell you in class or out of class that this mechanism is important, this is a type of mechanism question you would see. So here you have what? You have a tertiary alkyl halide, butyl chloride. And you have water. Is water a strong nucleophile? No, this is a weak nucleophile. And you see that you're even generating acid, and it's obviously a substitution. You're going from an alkyl halide to an alcohol. And the chloride's your leaving group. So this mechanism is clearly an SN1. So when we think about mechanisms for SN1, we need to be thinking about carbocation. So we do a little brainstorming. Carbocation, we think about tertiary alkyl halides. And this is actually called a solvolysis because your solvent is also breaking your bond. Okay, so the first step is you have a leaving group. Remember, this is your rate determining step. This is your slow step. And so the chlorine leaves, and it forms a tertiary carbocation. Okay, so you need to get that, and that will be worth so many points. And then your chloride has left, and you make sure you put in your lone pairs and your formal charges so you can get all your points. You put that in the box because it took the electrons. Okay, that's the first step. And the second step, there's intermediate here, tertiary carbocation. So that was slow step. This one's fast. Now you have the water nucleophile. So the lone pairs will go straight into this unhybridized. You'll remember this is unhybridized p orbital because it's an sp2. And when that happens, you get, so let's go ahead and draw this sp2 carbocation. And then the water comes in and you get O. And you still have both H's there, so that's a plus. Because oxygen there has, let's draw the lone pairs, has one lone pair and 3 bonds. Gives it a formal charge of plus. If you have a plus on your reactant side, then you need to have an overall plus on your product side. On number 1, you had a neutral. So on the product side, you have to have a neutral. Well, a plus and a minus is a neutral. Okay, and then the next step, you basically just copy this here. And the water will take one of these lone pairs and deprotonate. And that's how you get your product. And that's kind of how you fill in the mechanism. Okay, this problem says draw the major product for each of the following reactions. Be sure to indicate the stereochemistry of the product if appropriate. So this is problem number 28. So what do we have here? Osmium tetroxide. This is alkenes, and these alkenes are chapter 8. This is a review of chapter 8. So the first reaction, do you all remember what osmium tetroxide does? Osmium tetroxide does a dihydroxylation. So basically, and it says indicate stereochemistry. So this dihydroxylation is going to be cis. So that puts that, it's going back. So there's your cis diol. Okay, so that's number 1. Number 2, you have another alkene. Now, this benzene is not. Okay, we're going to deal with that in chapter 16. And you're doing HBr. Dichloromethane is just your solvent. So here we have the alkene takes a proton, and you remember this is Markovnikov's rule. Markovnikov's rule. And do you remember Markovnikov's rule? So basically, where's your proton going to go? Is it going to go this carbon, or is it going to go this carbon? Well, it is going to go to this carbon. So you already have 2 hydrogens there. Now you're going to have this hydrogen added, and that's going to give you the most stable carbocation. So now you have sp2, stable carbocation, the most stable, and that is a tertiary carbocation. So whenever you make a carbocation, you need to classify it, because that carbon is connected to 3 other carbons. That makes it a tertiary carbocation, the most stable. Markovnikov addition. So now you have the bromide, and you look for another nucleophile, because remember, if you have water in there or an alcohol, that could be your nucleophile. But here you have bromide, and then those electrons are going to go right into that empty p orbital, unhybridized p orbital, and make a bond. So, and that is your alkyl bromide. So you went from an alkene to an alkyl halide. And the funny thing is, I wonder how stable that would be. That is your product here for number 2. And is there anything? Okay, so that's your Markovnikov product. Markovnikov product is going to be your most substituted product. So the bromine is on the most substituted carbon. And it's because of this intermediate here that I'll draw like this. It stabilizes the carbocation on the most stable carbocation. Okay, your next one. Do you recognize that reagent? You got to recognize these reagents. So you have, what is your substrate? Let's classify that. Yes, so we're dealing with another alkene, chapter 8, review. And you have NBS. Do you all remember what NBS is? That's N-bromo succinimide. So that structure looks like this. And what that does is it generates a free radical. It generates bromine free radical. So that's bromine free radical. Now remember, bromine radicals are more selective. So if you're going to work in the laboratory, this is a way you can brominate a compound. I can tell you right now, from 10 years of working in the laboratory, this is about the only free radical reaction you want to do if you're trying to do synthetic chemistry, unless you're going to do polymerization and polymer chemistry. So the NBS generates the bromine radical. Bromine radicals are selective. So now the question is, when you look at this alkene, is where is it going to add? So this is the initiation that I just kind of drew. So when you're drawing free radical mechanisms, you got to remember propagation. It's kind of how you write the mechanism. Initiation. So what's going to happen here is you're going to have a half arrow, because you're dealing with only one electron, and it's going to form a bond, see the half arrow, with one of those electrons, and then the other electron is going to go. Now, is it going to go to this carbon, or is it going to go to that carbon? And I'm here to tell you it's going to go to this carbon. Do you know why? Because that's going to be your most stable. So we'll just go ahead and draw that radical there on that carbon. And then we'll go ahead and draw your new bromine covalent bond here at this other carbon. And then I like to count carbons, make sure I drew it right. 1, 2, 3, 4. 1, 2, 3, 4. Okay, so we're still doing propagation because we have a free radical. And in your propagation steps, your new free radical is going to have to generate another radical. So this can keep on going. So that free radical is going to react with another bromide. And here, the way we have it, you could just draw it with the bromide here. Actually, I don't like that. What I don't see here is HBr. And you would throw in a little bit of HBr in this reaction. Like I said, I just pulled these from some old test exam for a nice review. So here, it's going to now pick up that hydrogen and generate that free radical. And so now you have an alkane and an alkyl halide, because that hydrogen went there. And that is your product. And you generate another bromine radical. And you don't have to do termination unless it asks. So looking at this product, this is an anti-Makarnikov. And that's why that's important, because you see the bromine here went to the less substituted carbon. So this went to a secondary carbon, and the hydrogen went to a tertiary carbon. And that makes it the anti-Makarnikov product. Okay, and the last one is bromine. Okay, so let's redraw that one. So let's do it over here. So this one, still you're doing alkene, and you got bromine here. And is it going to be free radical? Let's take out the H nu here. Okay, let's not make this free radical. For one, let's just not make it free radical, because it's not going to be much different than what you just did. Okay, so now you have this alkene and you have bromine. And the reason why this is important is because this is going to show you that alkenes make a bromonium ion. So let's see what that looks like. This is that carbon. The bromonium ion is this ion right here. And that was an important concept right there. And so the bromonium, I'll write it down. Bromine, bromonium ion. So it's a 3-membered ring. And now you have this other bromine nucleophile. And it's going to open this ring. And now this is going to open in a it's going to open at this carbon. And let me tell you why. Because you have a plus charge here. And so this is positive. This is going to be your more stable positive carbon because it's more substituted. So that's your tertiary. The other one is a secondary. And so when that happens, it opens up and you get anti-addition because it comes in from the back side. So let's see if I can rewrite this product. 1, 2, 3. 1, 2, 3. And so it went here, and then you also have the bromine here, and then breaks that bond 1, 2. 1, 2. So 1, 2, 3, 4. 1, 2, 1, 2, 3. So what did I do? 2, 3, 4. 1, 2. I have run out of space. I don't really like this here. Okay. I'm having trouble erasing. Okay, so well, anyway, the bromine comes in from the back side and opens this. So then you have a anti-dibromide compound. Okay, so this is more alkene and alkyne. We will save the alkyne problem because we have not done that yet. That's chapter 9. This one here, in alkene, so you see your functional group alkene, call that number 1. And what is that? CH3, you see it's O3? Okay, so what is that? And that's the first thing that happens. That's a per acid. So per acids with an alkene make epoxides. So, and that's going to be an acidic epoxide. So what's that mean? That means it's going to probably get protonated. Now, the second thing you have is methyl, that's CH3, sulfur, and then potassium. Whenever you see a potassium, go ahead and make a plus because it's a positive. This is kind of like, this is almost exactly like a methoxide, except it's a sulfoxide. Sulfurs behave a lot like oxygens, so you can treat them like such. Now, this is going to be, now the problem is here is, let's not make this acidic. This is kind of confusing, because if it's acidic, it's going to open one way versus the other. But because this is an SN2, and it's basic, it's going to come in the least hindered. So when you think of SN2, you need to think of least hindered. So you've got two choices here. You can open this epoxide because of the ring strain, either here or here. So epoxide's open because of the ring strain, and that is, this one's going to be SME, which is your methyl, and that's going to come from the opposite, so then you're going to have OH, and here you're going to have CH3. And we're going to be talking more about epoxides in chapter 10. So if this nucleophilic opening of the epoxide is kind of new to you, that's okay. Like I said, we're going to be talking about that a little bit more. But definitely you should know that alkenes get epoxide using per acids. Okay, the next reaction, number 3, has a Newman projection. So what I would do is, and you see the reagent terp butoxide. The O-tosyl is a tosylate. That is a great, one of the best, world's best leaving groups. Okay, now, if you notice that, T-butoxide is going to do an elimination. Okay, and it's going to eliminate from a carbon that's next to it. So let's see what that molecule looks like if you drew it out. The phenyl is next to this carbon, the carbon you see. See if I can draw that. So that carbon, and that carbon has a tosyl group on it, and it has a hydrogen, and then it's connected. This thing in the back, we'll make that a blue carbon, and that's got 2 hydrogens on it, and then it's got a CH2 and a phenyl. So if this is your leaving group, the tosylate, it has to take a hydrogen. T-butoxide does not do nucleophilic addition. It's a base. It's a strong base. It's a hindered base, okay? So we're definitely looking at an E2. So when you look at an E2 reaction here, with tosylate leaving, the base has to take a nearby hydrogen from the nearest carbon. So phenyl doesn't have one. So it's definitely going to be this blue. And so T-butoxide is going to take this proton, and this is going to leave. And so your product is going to be a phenyl, CH, double bond, CH, CH2, phenyl. So that is your product for number 3. Number 4, this is not a peroxide. See, it's just acetic acid and sulfuric acid. So what's going to happen? You are basically going to add an acid. I want to say this is the Pinnacle. Let's see, chapter 8. Let's look at chapter 8. And I don't think that I'm going to require you to know that one. And the reason why, it doesn't have water, so it looks like it's a, so we'll just hold off on that one. Okay, so you can just scratch that one. Okay, the next one is what? What is the name of this? This is hydroboration, so you need to know that, boration, and then oxidation. Hydroboration comes from the BH3. Now this you can buy. It's in a bottle with THF, which is pretty impressive considering borane is highly flammable. And hydroboration, imagine a hydrogen and then BH2. And I like to draw it like this. It helps me remember because this portion is going to go to one of the carbons of the double bond and the hydrogen is going to go to the other one. And then oxidation helps me remember that it's got to be hydrogen peroxide because that's an oxidizing agent and base. So when we look at our substrate here, we have an alkene. We need an alkene, so let's redraw the alkene. And this is 1, let's write the name here, 1-methyl cyclohexene. Okay, so 1-methyl cyclohexene. Now, the boron, this is going to add to the least hindered. So the boron adds to the least hindered carbon, so it's going to add to this carbon here, and the other carbon is going to get this hydrogen. And then hydrogen peroxide is going to replace the boron with an OH. And so we're going to make an alcohol, and it's going to be stereospecific, meaning it's going to be syn or cis addition. It's going to add the hydrogen and the OH on the same side. And it's going to be anti-Markovnikov because it's stereospecific because the hydrogen and the borane add at the same time. So this is going to be BH2. We can just draw like that, and then the hydrogen is going to add on at the same time on the same side, and then we put our CH3 at the top. Now, The oxidation, the borane gets oxidized to hydroxyl. So you end up getting a trans. We can go ahead and even name that. This would be trans 1, 2, 3, 4, 5, 6, trans 2-methyl, cyclohexane, all. And that would be the anti-Markovnikov product because it's the OH added to the least substituted carbon, which was a secondary carbon instead of a tertiary. Okay, draw the major products of each of the following reactions. Be sure to indicate the stereochemistry of the product if appropriate. Okay, so what do we have here? We have water adding to yeah, and I wouldn't just give it in water. Okay, I would give you a different reagent. Would water displace the alkyl halide? And I'm not going to give you something that I find somewhat tricky. I mean, could that be no reaction? Or would the water displace the the iodide? So let's not worry about this. This reaction is SN2. And so you have a primary alkyl halide. And you have a dimethyl sulfide. And so basically it's going to do a backside attack and you're going to get 1, 2, 3, 4 with the sulfur adding like so. The next reaction, this is methoxide. And you got a Newman projection. And the question is, do you get elimination? You're probably going to get, and you have 1, 2, you have a tertiary alcohol. Tertiary alkyl halide. Can you see that that's tertiary? If you need to, you can redraw it. This carbon has a bromine and it has a CH3. And then it's connected to the back carbon, which has a hydrogen, a phenyl, and a CH3. And so this is going to do elimination. It's going to do an E2 because it's tertiary substrate with a methoxide. So it's going to come, and this is the only proton that it can take, and it's stereospecific. The bromine is your leaving group. You're forming an alkene, and what does that look like? Now, the question is, did I draw the right product? Okay. Notice that I have drawn the phenyl groups as trans. Is that correct? Well, this is where you have to look at your stereospecific deprotonation and what is the conformation that proton is going to be abstracted. And that proton has to be extracted in the anti. So let's redraw that and check. So you have bromine, and we can leave a bromine there. And what I do when I do these, I only rotate one of these. So I either rotate the front or the back. So I'm going to rotate the back, the blue. And as you can see, if I rotate it 60 degrees, then we're eclipsed with bromine. Then I can rotate it here, but I need to rotate it all the way until it's anti. So I need to rotate that hydrogen there. And when I rotate that hydrogen there, this phenyl is going to be there. Is that right? And that methyl, call that methyl is going to be there. And so you notice the methyls are on the same side and the phenyls are on the same side. So this is not right. It should not be trans. since these are on the same side, it should be, when you get elimination, you're going to get cis. Okay. This reaction would be no reaction, and that's because you're not going to get backside, no SN2 backside attack on a bridgehead carbon. Okay, you're not going to get the right orientation. So this is a bridgehead carbon, and so that is not going to happen. You can't get into the right, you can't get the backside attack. So no reaction. Okay, this one here, see you have bromine and H nu. So basically you're generating a bromine radical, and then what happens is you get bromination here. So your initiation is such that bromine adds, and bromine's going to add to this carbon and give you that radical, because this secondary radical is more stable than a primary, and then it's going to react with another bromine and form another bromine bond, and your answer then will be a dibromide. Okay, and then the last one here is alkenes. So this is what chapter is this? Chapter 8. You have a transalkene, you have osmium tetroxide, and then you're going to break up the osmate ester with water and sodium sulfite. And notice that that stays trans, so it's going to stay trans. So you're going to have your diol on the same side. So the diol is going to be on the same side here. That's how I drew these on the same side with the bonds coming at you, because you're going to get to the cis diol. Okay, circle the most acidic proton in each of the following compounds. Recognize acidic protons is important. So you got to know, what do you have here? This is an alkyne. An alkyne. So terminal alkynes have a pKa of 25. Which proton is it? It's that proton right there. Okay, the next compound, what is this? This is acetic acid. Acetic acid. And that is a carboxylic acid. Do you see the carboxylic acid? And that pKa is about 4.7. That's your proton that's acidic. That's the one that will be removed to generate an anion. Okay, this molecule here. Well, it also looks like this. You got a 5-membered ring, and then you have, what is this? OCH3. This is an ester, okay? And well, you probably don't know this yet. We haven't talked about this. And this is going to be organic too. So basically, this proton here is your alpha proton, and this is your most acidic proton. And this has a pKa of, I want to say 20. So that proton there. So you wouldn't know that yet because we haven't talked about that. And we'll talk about that probably around Mountain Day or a little bit after Mountain Day. Okay, answer the following questions. Depronation of acetone gives the compound with the formula C3H5O-. How many total valence electrons does this have? Okay, this is about Lewis structures. So we've gone back to chapter 1. You got 3 carbons, so that's 3 times 6 is 18. 5 hydrogens, so that's 5. 1 oxygen, That's 6. These are the group numbers. And then you have a negative charge, so you add 1. So that would be, is that 30, 12, 20, 30. 30 valence electrons. So 30. Draw the best resonance structure. Look, they've already started here. CH3, CH2. And you see carbon has here 2 bonds and 2 lone pairs, so it has a negative charge. When you're doing Lewis structure, you want to have all your lone pairs in. Now, these resonance, these lone pairs, can go to an sp2 center, which is that carbon there, and then the pi bond electrons can move up. So, when you're drawing resonance structures, it's only the electrons that move, and they move in unhybridized p orbitals. That's why it's got to be sp2. And you're going to make a double bond here, CH2. Now, if you start with a negative, it's got to have a negative, so that's kind of a check. Include all unshared pairs of electrons and formal charges. So we did that. That's fine. Indicate the following values of each atom. Okay, we're looking at hybridization and bond angles. So I don't care if you give a rough estimate. The leftmost carbon, so this one. Well, that carbon has 3 hydrogens and a carbonyl. So it has 4 things attached, 4 groups. That's going to be sp3. 3 plus the 1 there is 4. 4 things, it's sp3. So sp3. And the bond angles are about 109.5. I have that memorized. The rightmost carbon. Okay, the rightmost carbon is this carbon. Now, it has how many things? Well, you call that 1. That's 2. So 1, 2, 3. Well, let's look at it here. 1, 2, 3. So it has 3, so it's sp2. It has to be sp2. That's how it's going to, it has to have an unhybridized p orbital, or it cannot do resonance. And sp2 is about 120 degrees. Memorized it. The central carbon atom, that's definitely sp2. You can see that it has 1, 2, 3 groups. You don't worry about the double bond. So that's sp2. And so that's 120 degrees. 120 degrees is planar. The oxygen atom, because the oxygen atom is participating in a double bond and resonance, so you got 1 group, 2 group, 3 group. This oxygen atom in this molecule is an sp2. So sometimes through transition states, these carbon and oxygen atoms can rehybridize from sp2s to sp3. So, and that will determine its behavior chemically. Okay, circle the achiral structures in the list below. Okay, well, achiral means it has no asymmetric carbon. Okay, and if you remember in Chapter 5, an asymmetric carbon is connected to 4 different things, 4 different groups. So, and when you're doing a ring, if you can go and, I'll draw this one out. If you can go and meet, so this is one thing that's different, that's 2 things that's different because hydrogen is not an amine. But if you can go to each one, these are the same, these are the same, and these are the same, and you meet in a ring and you haven't seen anything that's different, that means it's achiral because you do not have an asymmetric carbon. You have no chiral carbon. You don't have no asymmetric center. So that would be achiral. Okay, this molecule here, these are cis, and they have a plane of symmetry. So I would say that's achiral. Okay. Also, you can look at it here. These go the same, these go the same, and then they meet. That's another test. I like lots of tests, especially if I'm going to be tested on something. So you can say, okay, let's look at this carbon. These two are different. So you go here, these are the same because you're going out. You could even just do it like that. And then you go here, and those are both methylenes. And then you go here, and you meet. And when you meet, they're the same thing. So that makes them achiral. Okay, the next molecule here, once again, it goes and meets, so that would be achiral. Okay, number 34. Describe the relationship of each pair of structures as conformational enantiomers, conformational diastereomers, configurational enantiomers, configurational diastereomers, or homomers. Are they the same? Are they identical? When you're talking about configuration is RS. Okay, R or S. So whenever you see configuration, conformation is it in the chair? Is it in the staggered? Is it the gauche? That's a conformation. And diastereomers means for something to be a diastereomer, they need to have more than one asymmetric carbon. So when you look at this first, okay, so you're just basically comparing these two. And you see that they're both 1,3. 1,3 diamino cyclohexane. And one of them, this, because you can see that if you drew your axial down, that this one is, what is that one? That one's cis, and this one is trans. So if they're trans and cis, these would be conformational diastereomers. I can't say I really enjoy these questions, and we are reviewing them because this is a review of Organic 1, but you're not going to get, you understand stereochemistry, R and S, and naming. I mean, it's an important concept, but anyway, I'll keep my thoughts. Okay, so the next one, what do we have here? The relationship between these two. Well, let's see, what do we have here? I'm going to go ahead and draw it out. The phenyl, the bromide. You could, so you could draw the phenyl there. You could draw the CH3 coming at you if you want this at me. Okay, and you could have the bromine going back, and then this would be in the plane. So phenyl's in the plane, and then this carbon would be in the plane, and then this carbon would be in the plane, and then the phenyl would be in the plane. So that's in the plane on that line. And then if you look on the back, you have this methyl and that hydrogen. So hydrogen and bromine are on the same side. So that would mean you'd have to put hydrogen on the back. And then these methyls are close to each other. So that would mean you would put this methyl coming at you here. And so when you do the same thing with this one, if you want to do the plane, you could do if you want to do the phenyl here, you would go here, and then you go to the back, which is, in this case, this carbon here, and then bromine. So you do bromine here, and then if you put hydrogen coming at you, then on the back here you would have the CH3 coming at you. See how they're on the same side? And then over here you'd have the phenyl going back, and you'd have the methyl going back. Now what I would do is I would then name these. And so you'd have 1, do the configuration, 1, this would be 2, this would be 3. Okay, so that's S, but then it's R because methyl is coming at you. And then this one here would be, so you got a carbon, and so I think this is 1 because you got it connected to a bromine, and this would be 2, and then this would be 3, and that's R. And you don't have to flip it because you guys have hydrogen going back. And then here you have 1, 2, 3, and that's R, but you got the hydrogen coming at you, so you got to flip that as an S. And then here, bromine's going to be 1, and phenyl will be 2, this will be 3, so 1, 2, 3, and that's R, but the methyl needs to go in the back, so you'll do the backwards rule, so that's S. So because this is RR and this is SS, these are actually configurational, and I would say they're enantiomers because each one of these are opposite. So a lot of times when I'm trying to solve these, I actually do the naming, the R and the S. And if this had been like RS and then RR, that would have been a diastereomer. But because each one of these is opposite, that makes them enantiomers. Okay, this problem states provide retro and forward synthesis for the following compounds from the indicated materials. Show all reagents required. Now, it is very important. It's a good practice, and we will practice a couple of questions on retrosynthesis. And so initially you'll see where I will give you the compounds, and you can work from there. So you have to learn systematically how to break the molecule down. So what do you have here? You have 1, 2, 3, 4 carbons. How many carbons are you provided? 2 carbons here and 1 carbon there. So already 1, 2, 3, 4. You're going to have to add more carbons. What else? Functional groups. You have an OH and an azide. Now I'm going to guess that that came from maybe an epoxide opening. So, because that would give you the N3OH framework that you have there. So then the question is, how did you get the methyl? Well, if you do, so you can imagine that, so I'm kind of doing the retrosynthesis right here. How would you get the framework for this? So you could have CH3, and look at the stereochemistry. So it's trans. So if this came from the back side and kicked that open, so we'll have to think about that. So how would you get this? Well, how did you get this epoxide? Well, this epoxide would have come from an alkyne doing an SN2, and that would make the CH3, and then you can do that a second time. How did you make that? You'd have to react it with sodium metal, and so you react this again with sodium metal, and you form the alkyne, and it reacts a second time with the the bromomethane, and so then you get the alkyne here, and then you want to reduce this down, but you only want to reduce it down to an alkene. So do you remember Lindlar's catalyst? Lindlar's catalyst gives you a syn reduction. Remember catalytic hydrogenation? But do you want syn? So this is where you can do your stereochemistry. There's also the sodium metal in ammonia, and that will give you trans. So we will go with one, and then if that works, that's great. If not, we'll see. So let's go with Lindlar's. So Lindlar's catalyst, and you could write just that, is going to reduce that down to, put your hydrogens on the same side, and it's going to reduce that down to the alkene. And then the alkene through, let's do MCPBA, metachloropurbenzoic acid. This is your per acid. You can review that. That should make an epoxide. So the epoxide, and that's going to be a syn epoxide. So that means that these are going to stay on the same side because that's syn. Now you're going to come in with a sodium azide, which you learned from chapter 6 that that's a great nucleophile, and this is going to go into an SN2, and it's going to do a backside attack. And so when it does this backside attack, it's going to put an N3 there, and let's say this goes down. Well, let's go with, this comes from the top, so N3, and that's going to, so if that comes from the top, that's going to put that down, and that means this is going to be up, and that's going to be CH3. Now let's look. And CH3 up is good, CH3 down is good. So Lindlar's catalyst works. Okay, so you just practice, and the important thing is just to practice these and try to pull in. Okay, this is another retrosynthetic reaction, and it's telling you to use an alcohol and an alkyne. So an alkyne would look like this, and maybe we can just go ahead and put a CH3 there, because I'm thinking that's CH3. I'm thinking this could come from our alkyne here, and then an alcohol. Okay, so an alcohol, and so how about that? Would that be an alcohol? Okay, so this is what I do. I use this alkyne, which is 1, 2, 3, which is propyne, and then this benzyl alcohol. Okay, so that's an alcohol. Now, what I would do here, and you don't know this yet, so you wouldn't be able to work this, but maybe in the future, when we do you'll learn that you can do an oxidation reaction. So you can actually use PCC, and you can oxidize this to a benzylic aldehyde. And what you do know is if you take this alkyne and react it with sodium metal, then you make a nucleophilic alkyne, and this will attack a carbonyl, and then that will give you an alcohol, and it would give you the carbon framework that you're looking for. Now, the problem with this is we really don't want the alcohol early on. And we haven't talked about protecting group chemistry, but you would have to protect this because there is one way to make that cyclopropane, and this should be review. So how do you make a cyclopropane? That is in chapter 8, and it's your Simmons-Smith reagent, and it's a carbene. So you make a carbene, that's a carbene, and a carbene with an alkene. So you'd have to use an alkene. You could make this cyclopropane. Simmons-Smith is the zinc copper couple, and you make that with CH2I2. But anyway, this problem probably wasn't the best problem for review from the standpoint that might be something we might revisit around Mountain Day after you have a few more lessons. But I want you to realize every chapter we're going to do a few of these exercises where we're doing retro synthesis and forward synthesis.